Hello my dear students of class 12. Today we will be discussing about one of the colligative property, that is elevation in boiling point, and this is from chapter number 2. So elevation in boiling point is a colligative property. There are other colligative properties also, and one of them we have already discussed in our previous video. So elevation in boiling point is because of when non-volatile solids are added in a solvent, in a volatile solvent. So non-volatile solid, whenever they are added in a solvent, as we have already discussed in our previous video, there is always depression in what? There is depression in its vapor pressure. There is decrease in vapor pressure. So let's discuss about this briefly. Suppose you have a pure solvent here, which is a volatile one, and here you have a solution where you have added some of the non-volatile solid particles. So these non-volatile solid particles will hinder with the vapor pressure. So here all the molecules that are present in this A and B, in A, since only pure solvent is present and which is volatile, what will happen? All the molecules at the surface will be going to the vapor phase. They will be going to the vapor phase. Therefore, its vapor pressure will be higher. Now, here in this case, where you have added non-volatile solid. So here you have a solution in which non-volatile solid is added. Volatile solid particles are added. Okay. So now this solid particle will occupy some of the surface area and it will hinder in the evaporation, or it will hinder the solvent molecules from going to the vapor phase. Therefore, its vapor pressure will be less. Its vapor pressure will be less than the vapor pressure of A. Okay, this A vapor pressure will be high as compared to the vapor pressure of this container B. Now this will affect in the boiling point of the solution. So that's what we are going to discuss now. Now let's discuss with the help of a graph. Suppose this side you have x-axis and y-axis. Along the x-axis you have temperature, and along the y-axis you have vapor pressure. So as you go up, the vapor pressure will increase, and as you go towards the right hand side on the x-axis, what will happen? Temperature will increase. Now suppose we have a solution and we have two curves, vapor pressure curves. Now for solution in which solid particles are present, and you also have a vapor pressure curve for pure solvent. Now just now we had discussed the vapor pressure of pure solvent, which does not contain this non-volatile solid, will be more. Therefore, its curve will be higher. Suppose this is the vapor pressure curve for say pure solvent, and the second curve that you have is the vapor pressure curve for say solution which contains non-volatile liquid with non-volatile solute particle. Okay. Now we have obtained the two curves. For pure solvent, the vapor pressure curve will be higher, and for the solution which contains non-volatile solid, the vapor pressure curve will be lower. Now, suppose suppose this is the point where it is 1 atmosphere, and say at 1 atmosphere, the temperature that corresponds to 1 atmosphere for this pure solvent, from the graph we can obtain it to be here. Now this is this is for pure solvent, therefore this is P0, and this is temperature TB0. That means it is the boiling boiling point, boiling temperature of this pure solvent. Okay, for pure solvent you have this boiling point to be at this particular temperature. Now at this particular temperature, you can see that the vapor pressure of the lower curve, suppose this is AB curve and this is CD curve. Now for CD, you can see that at this particular temperature and at this particular, this is 1 atmosphere, where pure solvent starts to boil, the vapor pressure for this curve CD is somewhere here. You can see that. So this is pressure P. Okay. So please don't be confused. This curve is for the pure solvent, and at 1 atmosphere, you know the atmospheric pressure is supposed to be 1 atmosphere where it starts boiling. Its temperature corresponding to that is the boiling temperature for pure solvent. Now at this particular temperature, you can see that the vapor pressure, the pressure of this solution CD, which contains non-volatile solute, corresponds to this point, say P. That means it is not equal to the atmospheric pressure. That means at this particular temperature, this solution will not start boiling. You can see that the vapor pressure of the solution is lower than that of what? The pure solvent. Now at what time, at what point, not time, at what point will it start boiling? When the vapor pressure of this particular curve will be equal to the atmospheric pressure. So let me pull this curve this side. So for this curve to have 1 atmospheric pressure, the temperature, the point that corresponds to 1 atmospheric pressure is here, and you can see that if you draw it towards the x-axis, you can see that this is the temperature where this is the point, and on the x-axis where the vapor pressure curve of CD, that's the solution, will be equal to the 1 atmosphere. And at this point only, and whenever this point is reached, then only it starts boiling. Therefore, let's take the vapor pressure curve CD's, that is the solution, its boiling point is at TB. At point TB. At this point, only its vapor pressure, the solution's vapor pressure will be equal to 1 atmosphere. Then at that point only it starts boiling. So hope this is clear in the graph. So we can see that this is the increase in boiling point, that is TB minus TB naught. Therefore, see, elevation in boiling point can be calculated as elevation in boiling point of the solution will be, that is delta T. Okay, delta TB will be equal to TB minus TB naught. This is the elevation in boiling point. Yes or no? Now, this TB minus TB naught corresponds to what pressure? P naught minus P. Can you see that? So, instead of writing this, we can write delta TB TB will be equal to P naught minus P. Now, from our previous discussion, we have seen that P naught minus P is directly proportional to mole fraction of the number of moles of solid N2. Okay, N2. Therefore, this delta TB is directly proportional to N2. So this shows that this is a colligative property. Okay. So delta TB is directly proportional to M2. Now since the elevation in boiling point, how much it is going to increase depends upon the number of moles of the solute particles, the non-volatile solute particles. That means more is the number of moles of solid particle, higher will be its elevation. Its elevation in boiling point will be higher. So up to this point, I think it's clear. Now, experimentally, they have found that the scientists, they have found that this increase in boiling point, that is, elevation in boiling point, is directly proportional to molality, small m, molality of the solution. So, delta now TB will be equal to Kb, this is small m is the molality, okay, Li, molality. So now, this is found experimentally. Now you know the expression for molality. This delta TB will be equal to Kb, and you know molality small m will be equal to weight of the solid, that is W2. 2 is taken from solid. I have told you in previous video also. By the molecular mass of the solid into 1000 divided by the weight of the solid, that is weight W1. Okay, so molality is equal to weight of the solid divided by the molecular mass of the solid into 1000 divided by the weight of the solid. So this can be written over here in place of this m. So W2 by M2 into 1000 by W1. So from this expression, you will be getting numericals. Okay. Now, here this Kbm is a constant. Okay, or you can write it. This Kb is molar elevation constant. So it is known as molar elevation constant or abelioscopic constant. So you can refer it from your book. This is known as what? This molality. So molar elevation, because there is increase in boiling point, constant. Okay. And from this experiment, from this expression, you will be getting numerical. Please don't forget that. Here you might be asked to calculate the molecular mass of the solid particle. So if you are asked that, that means you can just write the equation in this form. M2 will be equal to Kb W2 1000 divided by Kb, not Kb, here you have W1 into delta TB. So from this particular expression, you can calculate the molecular mass of the solid particle Kb W2 1000 divided by W1 into delta TB. So from this particular expression, I told you, you'll be asked to calculate the molecular mass. So there are plenty of numericals which are solved as well as unsolved. Numericals in your book, please practice them properly. So in our next class, we will be discussing about another colligative property, that is depression in freezing point. Till then, practice properly and please keep revising whatever I